This is a public re-recording of a talk originally presented to Chrome GPU as a GPU brown bag talk. This project is not affiliated with Google, and the ideas presented here are my own. Glide to Vulkan, Gulkan. The motive and opportunity for this project is a video game. We all have our favorite game from childhood. For me, this is Star Wars Rogue Squadron 3D. I know every line of dialogue from this game by heart, every medal earned, every secret upgrade captured, and every bonus level beaten. Rogue Squadron came out 25 years ago today exactly. Since I love this game, I really wanted to stretch my Vulkan legs and do a port. I think I needed to satisfy my childhood curiosity on how this game worked graphically. I could have started with DirectX, but I've done DirectX professionally, so I really wanted to go arcane. So I chose 3dfx Glide. Just to provide some historical context, the API lists board configs. The Voodoo graphics card is listed right here. I played this game using DirectRaw, so I never had the pleasure of using any of these devices. I didn't know Glide much at all before starting this project. Glide is very much a graphics API of its time. The most important feature here to highlight is that Glide is a rasterization only API. This means that at the Glide API level, the triangles have already been clipped and culled and projected. There's no need to describe or define your vertex streams in Glide, for there is just one. It could be that you think you have proper Z, but that comment right there dissuades us of any such hope. There is depth, but it's certainly not linear or in any space that could easily translate into something that's useful. Further limitations to Glide is how our game Rogue Squadron uses the Glide API. So while it doesn't call any anti-aliasing functions directly, the submissions are on floating point, so this is more of a semantic limitation. Given my complete lack of experience with Glide, I decided to start with an existing Glide to OpenGL port. This port is open source, and it's called OpenGlide. Interestingly enough, MiniGL is actually the inverse of this, going from OpenGL to GFX Glide, and was used to support Quake in 1997. How are we going to intercept the Glide API from the live running game? All of us developers that are familiar with Windows know that very well that we can just do a DLL drop in the correct folder and we'll get a replacement. So when the game loads and then we are given the correct DLL name, it will get loaded and start calling our implementation instead of the system implementation. So OpenGlide implements Glide via GL. This is pretty simple forwarding type implementation. I did a minor bug fixes and some refactoring to get Rogue Squadron to work flawlessly on OpenGlide. Similar projects to this type of graphics interception, there are many similar types of projects, Angle being one of them. I was now ready to start making major structural changes to lead to the Vulkan implementation. The first restructuring here is so that the Glide implementation in green, such that we can compile a full frame by tracking the respective Glide state. Again, this is reminiscent of something like angle validation, which thank goodness this is on a much smaller scale. The frame is sent over through another DLL boundary to the Vulkan implementation. I call this Vulkan 3D because the game itself had 3D in the title, which was the custom of the time. Expanding out this green box a bit, we can think of the runtime as submitting simply a frame. The rendering API has multiple functions, but some of them are simply for startup. Some others are effectively just more draw commands. And finally, the swap is the actual frame submission. A frame is simply composited of draw calls and resources. A frame can be copied or moved, and its only non-local references are resources, and those resources here are only textures. The triangles are fully dynamic and resubmitted every frame in draw calls. So this structure is certainly not unique, and it is a very simplified version of a deferred command buffers found in many engines. As mentioned, the only inter-frame state here is resources, which are textures. One can easily replay the frames within regions where there is no inter-frame state changes. This is actually fairly common for a game like Rogue Squadron because it is a level loading style game. We want to render any frame at any time we want. To do so, we must recreate the resources for this frame at that time. While this is fairly easy to do, this actual part was not implemented in the code as it exists today. Finally, if there is any inter-frame dependencies that expect something to occur in a sequence, they will be thrown off completely. So motion blur has this dependency on the previous frame and behaves as though it has a sequential dependency on frames. So all of the captures from the game in this presentation were actually done using the frame replay system. This GIF loops, but actually the loop here is exactly what you see on screen when the replay is engaged. Within this replay state, I can then use other debug functionality, things like hotkeys, to visualize the graphics data, which is exactly what we're going to do next section. A side note is that one can do full Visual Studio Live debugging in all the code in this project. So one can set breakpoints, read variables, and then continue. And that, of course, is very useful. So I cannot cover all of Glide in this broad talk. So let's focus simply on what Rogue Squadron looks like in Glide. So we have the big reveal. So here's a frame for the first level of the game. And here in draw order is how Rogue Squadron renders the game. So the train is coming in. Note that I did not change the draw order. So my initial observations here is that for a game that has a real depth buffer, the drawing here is quite inefficient. The other thing that we can also see is that the blob shadows came in as separate draw calls and not actually implemented as something like a shadow map, which is pretty obvious for a game of this era. So we can also peel back the elements that make up the final composite. So here we're visualizing the vertex color for each polygon in the scene. Here we can see depth. This is linearized depth going out towards the distance in the terrain. There's actually a modulus operation applied here, so it looks like continuous banding with changing color. So we have a next scene, which is a classic Star Wars rendered Star Wars ship. So in this example, we can see the back to front rendering with most of the alpha blending being rendered last. So now taking a look at the elements that composite this frame, we have depth, we have vertex color, which we've seen previously, and then we have something new, which some call albedo, which is the color of the texture. These are combined together to make the final frame. The wireframe reveals actually very few triangles. This is expected. The exception here would be all the per quad text glyphs, and this proves that nothing really ever changes when it comes to game UI. So there are many kind of cool techniques used in this time period. So one pretty cool technique to improve the apparent geometric detail of low poly objects is reference alpha. So this technique has been slowly deprecated in favor of tessellation, or simply, as highlighted by the recent City Skylines game, excessive geometry. So these trusses here look like they have fine structure. And then the structure is seen in the depth buffer. But when we look at the actual polygons, there are very few. There's like 2. So this technique is used modestly in many places throughout the game. Sometimes we forget that rasterization is really just a mathematical trick. The modern graphics APIs allow us to forget this because they are designed around automating these tricks. So the trapezoid in this image is supposed to depict a single plane going way out into the distance, like a big ramp. The issue here is that the center of this plane is here in yellow, and not the linearly interpolated center in screen space, so in screen's coordinates. The solution here is, of course, to not linearly interpolate it, but to perspective correct interpolate the UVs. So because glide doesn't have Z or even this W, the vertex stream itself contains the perspective interpolating W. So here is the incorrect and then the perspective correct. It's worth noting that I initially didn't consciously fix this. I just sort of intuitively guessed that I needed to divide by W in the fragment shader, and it just seemed to work. So speaking of the fragment shading, let's talk about how glide does shading. So glide is fixed function. We can visualize this as many different parameters, some might even call them uniforms, combine in this great big box to produce a final color. So how do we combine them? This is a bit like asking how many functions exist for a function f that takes parameters a, b, c, d. The answer is basically infinite. Realistically, we have 2 ways of compositing and blending the ways of compositing and blending defined by Porter and Duff that were set out before I was born. So here we also have some common operations, some constants, and some selection even based upon, let's say, level of detail. And yes, it was not long after this time that we started to be able to program directly the fragment shader. It might have been due to the content pipeline, but Rogue Squadron 1998 does not perform complex fixed operations on the input textures. The notable exception here might be something like lens flares. What this really means is that only a mutating vector stream was really necessary for the graphics of Rogue Squadron 1988, as we saw from those frame breakdowns. Something else should also be noted here. The fog is enabled. When fog is enabled, the vertex alpha is used for fog blending. This dual usage limits the usage of vertex alpha in the game itself, as most game scenes will have distance fog because the game is based upon type of terrain simulation. So this project is called Gulkan, so we have to be talking about Vulkan. So the frame of Rogue Squadron is very simple. There are no special operations that shouldn't easily translate into programmable shading today. However, Vulkan itself is a challenge. Glide was stateful, and so is GL. Vulkan is stateless, or far more stateless and atomic. Yes, I am aware that of extensions to support dynamic versions of some of these states. The depth state is probably used for greater or greater than equal type operations for implementing things like blob shadows. Beyond the 600 lines of initialization code, the actual render loop here is very simple. So what we do is we fill in a vertex structure, shown here in green. We then start a render pass, and for each draw call, we conditionally update this pipeline state and descriptor sets. I always draw, and there can be hundreds of draws, but hundreds of draws is not really a problem for GL, and it shouldn't be an issue for Vulkan. The pipelines are created lazily, but live forever. The descriptors are refreshed every single frame. This is all very, very basic, but mostly works and allows me to render in the original draw order of the game. So by bugs, I mean errors that were my problem, but were perhaps not my fault. I was shocked that I could just sort of read outside the range of my vertex stream. This is even with validation enabled. So -1 is, of course, 4 billion, and that's 4 billion vertices. So to draw 4 billion vertices takes a huge amount of time. I was not actually sure what was happening on my machine, as this sort of wreaked havoc on the machine and knocked out my sound driver. Also, the length member of vec3 in GLM is a constant, which is kind of odd. And that constant turns out to be 3. This is quite a surprise. Oh, and use validation. So Vulkan design encourages wrappers and library code. It also encourages some pragmatic, but what I would call lazy behavior, specifically with things like descriptor sets. Over allocation via reasonable values is a common go-to, or even like many individual sets that contain single elements. I like that I have full control, more control, obviously, and I don't want to go back to GL, but it would seem to me that everyone now is just simply writing their own special version of GL. This is the most boring part of the talk, or should be the most boring part of the talk. Mine is on the right, so there are some gamma differences, and maybe differences between how the thrusters are rendered. Mine is on the right again. I think there are small subtle differences in the alpha and the red of the plasma. You can also tell it's mine, which one's mine, because I don't have 16-bit blending in my version. So this is a screenshot taken directly from the Steam store for this game. And then the next frame here is mine. And it literally could just be the next frame in the cinematic, complete with canopy, windows, and tint and everything. So we're done. Glide to Vulkan, or glide on Vulkan for Rogue Squadron 3D. But why stop here? Now that we have a modern graphics API or backing, perhaps we can add a few graphics features that have occurred in the last 25 years. Features that the Rogue Squadron developers might have dreamed of, but could not achieve due to technical limitations at the time. We have seen what this game looks like in full detail down to the wireframes. If we could, if we look at a list of graphics features or lack of features, maybe we can start to change how this game looks. In the 90s or early 2000s, games wanted more detail, but could not afford the texture memory that was required. The solution was to use these lower res tiling detail textures that only became visible when the primary texture became very blurry. These images are from Unreal Tournament in 1999. So with just a few lines in our fragment shader and another image view sampler, etc., we can get this effect in Rogue Squadron. This is a live image capture from the game. The problem is that when we apply this same texture liberally to all surfaces, it starts to look just like noise. This is because that's what it is. If we go back and look at how this looks like in Unreal, we can see that each material has a different associated detail texture, and that's pretty important. So to get better detail, we need a content tag. But given that we do not have the same memory limitations of the early 2000s, we could just replace all the textures with high-res textures. And if we're going to go ahead and do that, why not provide displacement or normal maps, etc. to all of them? So I didn't push any further down this line of modification for a multitude of reasons that will be highlighted at the end of this talk. Another graphical upgrade I pursued was to provide anti-aliasing to the entire game. A modern way to do this is to simply super sample, so that's what I did. Super sampling avoids some rare aliasing, but also makes bitmaps mostly unnecessary. The game gives off a very different vibe without the line aliasing. It's almost too clean. This too is a problem that I will highlight at the end of the talk. So PostFX became popular around 2005 when the graphics APIs allowed for render to texture. Bloom, which is a kind of simulation of HDR or tone mapping maybe, was famously overused at the time. So most of the PostFX would require, again, content-specific work, but one that could be done as is was motion blur. So instead of maybe wisely choosing to do this as motion blur reconstructed from, let's say, the image buffers, I thought it would be a much more interesting to try to reconstruct this motion from the polygons themselves. The geometry is actually a superior source of motion data when you think about it, but it's probably harder to deal with mathematically. There's also performance issues here, as the entire motion vectors for all vertices must be computed in much less than 60 milliseconds for all frames. Otherwise, we're going to start dropping frames just for this effect. As repeated often, Glide is a raster API. We don't have vertex shaders, and we don't actually have 3D geometry. We have post-clip screen space triangles. Triangles are clipped. The triangles that are clipped by the viewport also change every frame, as you can see here. What looks like a simple scene is actually a tangle of moving vertices, some of which are appearing and disappearing as the frame advances. To reconstruct pixel motion, the pixel motion of vertex, we first need to find the connectivity via position hashing. This means all the vertices of the same location will have the same ID. We then accumulate a single hash for the vert from all of its contributors. This gives us a relatively stable ID for each vertex in the scene for the current frame. This final vertex ID allows us to hash and find previous frame vertices with the same ID. It should be noted that these IDs are not globally unique. This is due to the repeat texture usages on multiple polygons, which is totally expected given that there may be the exact same vehicle in the same frame. The purpose of the vertex ID is to determine if they are clipped and then to use them cumulatively to form a single triangle hash ID. This hash ID is much more unique and is relatively consistent and consistent from frame to frame. So this is a colorized hash ID of all the triangles in the scene. Many are stable, but at any given time a vertex changes its connectivity, there will be a corresponding change, and therefore a change in the ID, which changes the color in this shot. These final triangle IDs will still not be unique, and thus we must use a type of weighted distance to determine which of the end triangles matches the previous end frame end triangles. State tracking of velocity between frames allows us to make a velocity projection of triangles to achieve a much tighter weighted match between frames. So the real challenge here is with the clip triangles. Imagine the side of the viewport moving to the left and is clipping this brown triangle, with the white triangle being the current frame and the brown, of course, being the previous. We can identify the triangles between frames, but if we just blindly use the clipped vertices, we would end up with the incorrect motion for these verts. The motion here would be likely 0. So the correct motion can only be obtained by doing a reprojection between the frames. This reprojection to the correct location involves solving a small matrix. When rendering the main pass, we now have an additional RGF16 color attachment that will be used to render out the result of this motion blur at a per mesh per vertex basis. In the newly created post effect pass, we then stretch out the pixels in the color buffer proportionally and in the to the intensity and the direction of the motion blur for that pixel. So here we have the original frame buffer. This is the motion buffer, or sometimes called the velocity buffer, with the motion to the right shown as red and the motion downwards shown as green. So we then take our original color buffer and we combine it to produce this. And yes, this is a real in-game capture. So even skeletal animation can have motion blur. So here you can see a machine moving its feet very quickly. It produces a motion blur. This is the visualization of the velocity buffer corresponding to that motion. This motion blur can also, be added to cinematics to give the game cinematics a more cinematic feel. And this is the motion blur velocity buffer that corresponds to the previous image. So the initial quality of the motion blur was actually quite low. One gets a lot of silhouetting type of effect because the blur does not extend outside of the object. This is based upon the implementation that was already described. It was difficult in my cursory research to find a good non-compute based motion blur, so I simply came up with my own. So here we have the original image, no motion blur applied. Here is the original motion blur, simplified motion blur with silhouettes potentially. And then here we have the more advanced motion blur that extends outside of the silhouetted object. I was quite satisfied with the results, but there are many other options and likely better implementations. I would highlight here that the non-buffer based motion blur that simply instances the geometry n times with blending would actually work very well with our per vertex velocity and compared to the buffer based velocity vectors. In this, this is the last shot, and what I consider to be the triumph of this project. We have successfully created a starfield motion blur effect in a 25-year-old game purely through a modern implementation of the original Glide API. To do a truly impressive graphical makeover would require the port to be content aware. And there lies the rub. I don't really want to put too much effort into this project, especially if it can never be released publicly. Perhaps I will take the risk on the 50th anniversary. I think that I have also learned something about the psychology of nostalgia. We dream of ultra HD versions of these older games, but if those dreams are realized, that realization will no longer actually be the game that we once played. So finally, my goal was to satisfy my curiosity on how this game worked graphically. And in doing so, after this project, I would say most of the mystery and perhaps some of the mystique around this game for me is gone forever.